Okay. Oh, thanks, Eric, for recording. I will figure out a way to sort of share the recordings with other students. Um, Hello, everyone. Hope you can see my chat. So can you guys see my chat and can you guys see my screen?
Yes to both.
Awesome. Okay, so up to now, we have been discussing about dynamic programming and shortest path problems. Let me open it up. Hold on. So we have looked at some algorithms, TopoSort being one of them, DFS being one of them, strongly connected components being one of them, the entire package of BFS and single source shortest path algorithms and all pair shortest path algorithms. And we have seen how different problems can require different such algorithms. Many such things are basically uh, in general algorithms that can be applied to different domains. If you guys remember, we had some discussion about the Floyd-Warshall algorithm, and where I said that APSP, that is the Floyd-Warshall algorithm, finds the shortest path between all pairs of vertices. Um, Quick question in the chat, or maybe Discord. I'll also open up Discord. Hold on. I have to share video links today. So, yeah, quick question. While I've set this up, what was it? Hmm. All pair shortest path, is it a best sum problem or a house sum problem? Think about it. In all pair shortest path, how is it a house sum problem? Are you asking how many ways are there to reach something? Are we answering that starting from a vertex? How many ways are there to reach all other vertices? Or are we saying that from a vertex, for any other vertex, find me the best sum for each thing, right? Zach, what do you think? We are asking for what is the best way to reach the particular vertices for all other things. Now, if you guys remember, I also discussed a bit about how Floyd-Warshall was similar to Kirchhoff's law. Kirchhoff's law basically says that, let us look at this diagram. This is definitely not a physics class, but by the way, do you guys know the latest joke about computer science and physics? You guys heard how ooh, Zach is typing. Yep, very good. So yeah, technically we are all physicists as well. Another dude got a prize in chemistry, so that's a first for computer science. You know, computer science did not have Nobel Prize. I said that right in the beginning of the class. So that's that. So yeah, so the point of Kirchhoff's law is that basically you have to figure out, given a point, current is coming in, current is going out. For this point, what is the total sum of current or electricity or whatever ampere value, right? So what is the total value of this particular thing? So do you see any similarity between this problem and Floyd-Warshall in a sense that essentially isn't this a house sum problem of Floyd-Warshall? You will be adding up all of the possible currents throughout all possible paths that is coming into this node, and essentially you will be subtracting all of the things that are going out of this node, and this essentially becomes a house sum problem, is it not? So it's a house sum problem version of the Floyd-Warshall thing, in a sense. Not in a sense, quite literally, if you write the code, there is matrix multiplication version of Kirchhoff's law, which pretty much is the same as your code. But yeah, don't tell physicists about that. So where was I? Uh, Coming back. So today, so we discussed about those sort of things and how some problems and what some problems and what not, not how what some problems. We will cover those again, and I'll ask you guys to do, for example, the how some version of knapsack. Can you guys tell me what will be the Howsam version of knapsack? Because knapsack was a best sum problem, but we will skip those for today, and we are just going to discuss one new algorithm, that is a minimum spanning tree. We have seen, or mathematically speaking, we are going to basically be discussing the concept of we are not going to be discussing the concept of matroids. I don't know. And essentially, we are going to be learning how to prove greediness. As in, you have a greedy solution to a problem. Why is your solution being greedy the best solution? Why is greedy the optimal solution or not? Okay, so that is the proof that we are looking forward to. We are going to talk about that. We have formulated problems as topological sorts, blah, 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 all of those things. Now comes the point where we are going to formulate problems as minimum spanning trees. Okay. So, first things first, in general, throughout the next 2 weeks, we are going to be bothered about these two things. That is, what is the cost function, because we are being greedy. So, quick thing. Can a greedy problem be Howsam problem? In general, no. In greedy, we are trying to optimize for something. And whenever we are optimizing for something greedily or wherever, it has a cost function. And in essence, that basically means these are all best sum problems. The only difference between normal best sum problems and greedy best sum problems is that for normal best sum problems, you need a recursive approach to greedily find, or sorry, to recursive approach to scan all possibilities like knapsack, right? Scan all possibilities and then figure out the optimal one. Best sum problems for greedy is that essentially you are going to know what the answer is and you do not need to search for the answer. Okay. So what I mean by that is, Corman had a nice uh, recursive problem. Can you guys tell me one thing before, until I find that particular thing? Can you guys tell me something? So for knapsack problem, do you guys remember, and type in yes or no in the chat? Do you guys remember how we asked the question from child notes? What is the best you can get from picking the thing? And what is the best that you can think for not picking the thing? And the child notes got you the answer. So my question is, was your answer dependent upon child answers? Everybody else, do you guys also agree? Right? So may I then say that the answer was dependent on the, so the answer not dependent, it is dependent, was computed after the recursive call, right? After the recursive call to children, right? Cool. Greedy means you know the answer before the recursive call. You guys remember head recursion and tail recursion? So that you know the answer before you ask the children. Does that make sense? So essentially, if you are writing a greedy code, knapsack code basically look like this, blah, blah, blah. And essentially you had your base case here. And then you have your choices here. And you basically listed out all of the recursive calls for choices, 1, 2, 3, whatever. And once you have that, your answer becomes some function of your choice results, correct? Now compare that to a greedy algorithm. Again, you'll have some parameters, obviously. You might, again, we are going to do recursive problems, so you will have a base case, but you already know the answer given the parameters right now, Then you can move on to other choices and decide upon them. You do not need to wait for the recursive calls of your choices to get the answer. Does that make sense? And it basically you will be returning answer, and here you are going to return answer on the way back. Does that make sense? That these two approaches, one is where I know the answer. Come on, do the nice thing. One is where I ask the children for my answers, and then once I get the results, I have a function, how sum, best sum, whatever sum, max, or whatever, and I get an answer, and then I return the answer because I'm waiting for the children to scan the entire space and then get me that fishing net goes around and does that space and gives us that answer. Compared to that, oh, by the way, I'm going to share with you guys a nice link that I found. I'll share that on Discord, I guess. Hold on. Nestedly recursive functions. You guys used Wolfram Alpha ever on this one? Yep. Okay. So this is Wolfram Alpha, and the guy behind Wolfram, Stephen Wolfram, loves to make graphs out of recursive functions. So here are recursive functions. These are nestedly recursive functions, which is just recursion. Don't worry about it. Read through it if you have time. And it has created graphs and stuff, and directed graphs and stuff, and plots and stuff. It's a fun read if you guys want to read it. It's about 100. But this is the sort of structure that you can generate using a recursive call for searching through the space, right? And essentially, this is sort of the visual I want you guys to have when we are talking about that fishing net, searching for all of those solutions in the space. And if you look into Eric Demain's videos nowadays, he has a YouTube channel separately. Maybe I'll share that later. Nowadays, Eric Demain is just he has grown a lot of hair, by the way, nowadays. But I don't know how. But yeah, nowadays, you know what his research area is? Where was it? So that's him. And you can go through his video. You don't need it for this class though. But essentially, what he is doing is figuring out the frequency of such structures by straight up frequency, the sound frequency of these structures. And every recursive graph will have its own sound frequency, and he's looking into that, which is a very weird thing to look into. Fun though. Anywho, coming back to this thing, we are today going to basically understand about greedy algorithms, and we need to basically understand the greediness as in still a best sum problem, but we know the answer before the thing. Okay, we will understand how to prove these things, and basically I have a proof checklist that you guys are going to uh, uh, submit your proofs along with like that sort of JSON formatting. um, but first, let us first discuss the very basic greedy village mayor problem. So what I'm going to do is I'm going to go to the slides in the course page, in course materials. We will look for greedy algorithms. And these are the slides that I'm talking about. We will also be learning a data structure that is sets, and you know how Python implements sets and stuff. So we will understand how sets work later. But these are the set of slides for greedy algorithms. We will be following these closely in a couple of days as well. But let us take a problem first. The problem is that you have, right. So let's say that you are the um right, this one works. So let's say that you're the mayor of this village. The village has multiple houses and it has edges connecting those houses. And essentially, what you want to do is to pay some money to maintain each of these streets. Now, the point is that you would like to pay as less money as possible while have all of the houses connected to this overall graph. So, which means that I can basically um, yeah, let's do this. Copy image. I can basically just decide that, you know what, being the mayor, I will be discontinuing this road, maybe this road, maybe this road, let's say this road, this one, this one, maybe this one. Oh, not this one. Uh, the, the, there, that's going out here, that's fine. And maybe basically you're figuring out crossing out these roads, essentially figuring out a road that can a set of roads that can be used to that you can maintain. Let's say that the set of roads with the cheapest cost that you can maintain, but still the village is still connected, as in there will not be a house without any connectivity to the graph. It might be a weird long distance connectivity to the entire thing, but as long as the entire village it has is connected, so it's not a disjoint graph, you are not making this into a disjoint graph, then that's fine. So for example, you can say let's maintain this road, this road, this road, and let's say from here we maintain this road, this road, and from here we maintain this road, this one. Oh, this one looks nice, so this one. And let's say for here we maintain this road. So basically, do you see that if we just maintain these blue roads, everybody here in the houses can still reach every other house, can still reach every other place. It just might not be the shortest path anymore, but it is still connected. Does that make sense? Connectivity, but not shortest path connectivity. Shortest path connectivity, but uh, lowest cost connectivity. Does that make sense? Overall cost of the thing will be the lowest cost. Okay, think of this as a server room and you're trying to maintain which servers would be connecting what. Let's say I want to watch a video from India, right? And YouTube needs to decide whether, so the video most likely is stored in India's databases, and YouTube would like to basically decide, is it worth the effort to copy the entire thing onto their databases here and then maybe show it to me locally or just stream it to me internationally, right? So it would need to maintain a lowest cost path in a sense, or lowest cost connectivity thing that would then sort of, you know, move around those concepts, right? So we'll be discussing about those things. This is the village problem and I hope that makes sense. The overall cost of the thing needs to be minimized. That's the thing. Okay, so right, where was I? Let's come back. So that's the greedy village mayor problem. We are going to come and talk about this thing, but before I do that, we'll come and talk about properties of trees in a second. But I have a question again. Sorry for bugging you guys so much, but I have a question. This connectivity thing that comes up, is it a tree or a graph? Meaning that will it have cycles? You guys agree it's a tree, right? And Will it have cycles? It will not. Why? What's the point of cycles? Well, I would want redundancy. I don't want that, right? I could create a cycle like this, which would make this into a graph. But now it's not the minimum cost connectivity. It is still connected, but I don't want this, right? The solution I'm looking for is the minimum set of roads that I need to maintain. And a cycle would mean there is a redundant path. This road, this house here could have very easily reached this house. Let me color this in red, assuming that we are planning on adding this road, but this house could have easily reached this house via this path. I don't care about the distance from this house to this house here. I don't care. I'm just maintaining the overall cost, right? So there is no point in adding this red line here, because the house can already reach there somehow, and I don't need to maintain that to maintain connectivity, right? So the solutions that we are looking for is that we are looking for a tree from our graph. That tree will be the set of edges that is the going to be the minimum total cost of maintaining that whatever thing. Cool. Before we go into those tree properties in the slides, let me show you the proof style mechanism that you need to submit your solutions in. So I will again be submitting or giving to you guys some random lead code problems or other problems, and you will need to now prove that the greedy choice, whatever the greedy choice is for that problem. In addition to that, you will have to prove why the greedy choice is correct, and that is called the exchange argument. Okay, the exchange argument assumes that you have an assumption, then you have a cost function, then you have an ordering possibility. We'll talk about those. There are usually two types of proofs. One is the stay ahead argument, which is usually the cost function argument, or the exchange improves argument. And then we will be drawing the swap if possible in those problems. So essentially up to now we have been formulating problems as shortest path problems. We are going to be formulating problems as a graph again, but as a minimum spanning tree problem. We'll compute the exchange cost to remove the part, cost to add a part, cost to adjust the solution for this new part added. And then the proof will just become, if the total cost plus the exchange cost is your total new cost, then if this total cost is after the exchange, you are better. So so let's say somebody gives you a solution and you say that, okay, this is not the greedy solution of the problem. And you have to show then that your greedy solution, once you do that surgery of edges, which we'll talk about in a second, once you do that surgery of edges, you will then have to show that after doing this, your cost is better, obviously. If you do that, then that is the proof of your greedy solution. We will have to see a lot of examples to get our head around this thing. The major two algorithms that we are going to cover is Prim's algorithm and Kruskal's algorithm. So firstly, let us talk about properties of trees. Let me have the chat window open on the side as well. Okay. So we are at the slides for greedy algorithms. Now, before I move on, I know we are talking about minimum spanning trees. If we actually go to the book, Corman book, Corman actually gives us hints in the greedy algorithm section. You will see that Corman discusses about minimum spanning trees here. And essentially, those are the problems that we are basically trying to formulate them as. Okay, so it's in the chapter 15, but it discusses about minimum spanning trees, which is chapter 21 here. That is the Prim's algorithm, Kruskal's algorithm, and how to grow a tree. We will talk about that once we get there. But for now, let us talk about and refresh our memory about some tree properties. Okay, so let us actually solve, let us actually solve this particular graph and get the minimum spanning tree of this particular graph. That way we can start talking about these problems. But before we do that, let us discuss some of those things. So we know that it is a tree. Um, So from your solution, you guys will agree that if your solution contains a cycle edge, If you remove that cycle edge from your graph, the graph is still connected and it is still acyclic and connected. So you can remove a cycle edge as we discussed, right? What were some other properties? There are some other properties, we'll come to that. Three properties, I believe. So the formal definition of a minimum spanning tree, what is its input, what is its output? So its input is a graph, an undirected graph as we saw, with edge weights for any edge E. The output is a tree with the same set of vertices as the graph and a curated set of edges E prime, where E prime is a subset of the edges E that minimizes the total weight of the tree. The weight is defined by the sum of all edge costs. Okay, so you are trying to minimize the total weight of the tree, that is the sum of all edge costs. So if we look at this particular problem, let's take this graph. So for this graph, can I draw stuff here? I don't know. Okay, so let's say we have this graph and I'll copy. So let us actually go and walk through this particular graph and we will be figuring out the minimum number of edges required to keep this graph connected. So let's say that, so I'm going to talk about an algorithm. This algorithm is the Kruskal's algorithm. We need a visual for both Kruskal's algorithm and Prim's algorithm. So let us first look into that. So this is Kruskal's algorithm. It will get reset in a second. Hold on. It's one of my favorite images, but hold on. So what Kruskal does is assume that this is a graph. Everything is connected, but nearest has less cost, farther away edges have more cost. Kruskal basically will be adding the edge with the minimum cost every time unless it creates a cycle. If it creates a cycle, it will skip that edge, but it will always pick the minimum edge out of all of those edges, and then it will basically be adding that. As you can see, this one was creating a cycle, so it is skipping those, and the things that are not cycles, it is basically adding those, right? So this is Kruskal's algorithm. We will use this algorithm now to solve this particular graph and figure out the minimum spanning tree. But before I do that, let me show you Prim's version of the algorithm. Prim's does the same thing, but it is more like Dijkstra, as it is growing outside. Okay, so it is basically maintaining from this starting node, and it is only going to add the minimum most edge outside of this boundary. So Prims is increasing the boundary. Kruskal, on the other hand, is more of a Bellman-Ford style, that the ordering does not matter. We are basically going to randomly pick smallest edges and just add them if they do not create a cycle. Okay, so let's follow Kruskal's algorithm for this thing. Out of this thing, just to check if you guys are paying attention, out of this thing, can you guys tell me which edge has the minimum most cost? Could you please type it out in the chat window? AC has the minimum most cost. So I will pick AC, brush, color, blue. Yes, this is fine. Can I not? Why can I not? Color, brush. I have to select the brush. So you, yeah, why not? So this is the edge that the minimum most cost. What's the next one? Well, the next one is CD. Correct? Now, what's the next one? The next one is AD. Now, adding A to D has a cost of 3, but do you guys see that it would create a cycle? So we are not going to be considering AD. I'm going to color this red. Okay. Now, the next one in question, we have options. We have AB, we have BD, we have CF. Do you guys agree with these three options? That is the next set of options that we are looking into. Yes. So we are going to just pick one of them. Doesn't matter which one. Can you guys type out your choice? Yep, there you go. So we will do CB. Let me use a finer pen. Hold on. This one's a stupid pen. So we used this one. We used this one. And are skipping this one. And we are going to be using, what did you say? CB. So I guess this was C. So this one was allowed. The next, remember, you basically were given a list of edges. And if we go to the Kruskal's algorithm code here, you see that what it says. Sort the graph edges by weight, loop through the edges one by one in ascending order of weight, test whether adding the edge creates a cycle. If it does not create a cycle, add the edge to the forest, right? Combining two trees or more, two trees into a single tree. We'll look into that later. But yeah, so now since we sorted all the edges, we just considered CB, but we then would be considering AB. AB is not going to be a thing because AB creates a cycle now, so skip that. Then let's say we are trying to look at BD. BD is also not going to be used because BD is creating a cycle. So then we are going to try to see CF. CF is the next in line. Well, that adding that edge does not create a cycle. So we will have that. Now, after that, we are looking at 5 and 6. So EF comes in and we have this particular tree that is the minimum spanning tree. Okay, so I am going to maybe use a recolor this thing with this solution, but with a smaller thickness. So the edges that we are using is this, 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 this. We used this one, I think, yeah, and this. Okay, so given this, can you guys tell me what is the total cost of maintaining this tree? Yep, 16, right? Now, think of an offer from me that says that, okay, you know what? You should be adding, instead of and doing this, can you maybe swap an edge with another? So for example, can I say I can swap this 2 with, let's say, yeah, with this BD. Do you guys see that if instead of 2 we have 4, the cost will go up to 18? The tree is still connected. There are no loops. Cost goes up to 80. So that is not the minimum most cost. What if we added this instead? Well, if we added this, we could remove either this A to C or we could remove this C to D. Well, either way, it in order to still keep it connected, we have to either remove one of these two. Either way, the cost will go up. It cannot go down. It is just what would be the cost if I removed, let's say, this one instead. So what would, do you guys, again typing out the formula? So the new cost will be the current cost 16 minus the plus the edge cost of 3 minus the edge cost of 2. Do you guys agree that this is the new cost, which is going to be greater than 0? Oh, greater than 0, right? So that is the proof of a greedy algorithm. That is, if you surgery out an edge and introduce a new edge, that is called the cut and paste property. And this argument is similar to our min coin change problem argument. If you guys remember the min coin change, we had three coin types. One was $1 coin, $3 coins. No, I think it was $5 coins and $7 coins. And the point was to find out the optimal way. This problem here is basically literally the shortest path problem. You have to search all possibilities. It cannot be solved greedily. But if I change the coin denominations to 1, 5, and 10, now this problem becomes greedy. Why does it become greedy? Well, I can always, so given a solution, let's say that the solution is for 13. So given a solution for 13, let's say my target amount was 13, and the coins that I picked, assumption wise, is 5 plus 5 plus 1 plus 1 plus 1. That is the solution for 13. Now, do you see that I can always swap out a part of this solution and make the two fives? Whenever I have duplicate fives, I can swap out that part of that solution into a smaller solution by just swapping out that solution for this new one. This is the same idea, the cut and paste property. You are basically going to say that your greedy method stays ahead, or your greedy method is going to not ruin the solution, and that is why greedy methods work. So we have to learn how to prove those things, but before we do that, let us just look into Kruskal's algorithm and see how that is proved. So first property is removing a cycle edge. So we are going to discuss about three properties first. So removing a cycle edge cannot disconnect a graph, so the solution must be connected and acyclic. Undirected graphs of this kind are called trees. The particular tree we want is the one with the minimum total weight, known as the minimum spanning tree. Total weight not from a source node to all other nodes. No, no, no. Total weight overall from the graph for maintaining the thing. Here we are not finding the shortest path from A to all other nodes. No. That would have also gotten us a tree, but that would be a different tree. Here we are looking for the tree that is minimizing the sum of all edge costs. That is it. The particular tree we want, examples, the sum of all edge costs is the thing that we are minimizing. Okay, we are giving a set of edges or returning a set of edges where we are minimizing the sum of all edge costs. There are two algorithms, Kruskal's and Prim's. Kruskal says repeatedly add the next lightest edge that does not produce a cycle. So it's basically simply going to pick whichever edge is cheapest. So it needs to sort the edges first. So that is n log n time complexity. And then it is going to add edges into the solution. So let us go back to the solution. Okay, so let's say we are here. Now, yeah, let's say we are here. Can you guys tell me which edge are we going to check next? Is it CF? So the point is that I have to do two things. One is to sort all the edges from top from in ascending order, and the second thing is I'm going to be adding edges to my solution, and while I'm adding, I need to check for cycles. So how do I check for cycles will be where we are going to use sets. So we need to learn how to implement a set data structure as well. We are going to maintain sets and of trees, and we are going to maintain that to detect cycles. So there is two parts to it. The time complexity coming in from the sorting part and the time complexity coming in from the set checking, membership checking part. Okay. So we saw this one. We added edges and we got that property out. And now, so let us, before we introduce the cut property, let us introduce some topics about trees. So a tree is an undirected graph that is connected and acyclic. Much of what makes trees useful is the simplicity blah. It satisfies the following properties. A tree on n nodes will have n minus 1 edges. Even a path of n nodes with a single path is a tree. It will have n minus 1 edges. But even if you look into a tree, every node is connected to one other node using an edge. There are no cycles in a tree. And since there are no cycles in a tree, n nodes need to be connected by n minus 1 edges, right? Property 3 is any connected, the reverse of the thing, any connected undirected graph with v minus 1 edges is a tree. As long as the graph contains v minus 1 edges and it is completely connected, as in there are no vertices that are not out there unconnected, then it's a tree. Property 4, an undirected graph is a tree if and only if there is a unique path between any two pair of nodes. So between any two pairs of nodes in a tree, there has to be a unique path. You cannot find another path going there because that would mean a cycle, and we do not have cycles in trees. The cut property says that suppose edges x are part of some minimum spanning tree of this graph v comma e. So edges x are part of this blue edges, right? It's part of some minimum spanning tree of a graph. Pick any subset of nodes S for which x does not cross between S and not S. Let E be the minimum weight edge across this partition. Then add this edge to be part of this minimum spanning tree. As Eric said there, the next edge to be considered is CF. Why is that? What is our partition here? Well, our partition is the set of vertices connected by the blue edges, and we are asking what is the next edge to be added. What is the next edge to be added? I cannot partition it here because this edge here is pointing to the same set in a sense, right? CB is now pointing, C is in set 1, B is also in set 1. So that creates a cycle. Instead, we would partition or visualize the partition like this, where we have two outgoing edges. Both of them go to some vertex, where one vertex is in this set, the other vertex is not set, right? So then if that is the case, then what cut property says is that you can add the minimum most edge across this partition, and that will be part of the minimum spanning tree. That is what this says. Okay. A cut is any partition of vertices into two groups, S and not S. What this property says is that it is always safe to add the lightest edge across any cut, that is between vertex in S and the one in not S, provided that X already does not have any edges across the cut. So why does the cut property hold? So let's say edges X are part of some minimum spanning tree T. If the new edge E also happens to be part of T, right? So let's say that you basically have some edges in X. Now you have a new edge E that is already part of this tree, then it is already in the solution, nothing to do there. I know this argument sounds weird, but this argument will come up very often, that when we are proving problems, that if the solution, your solution is already part of the assumed solution. So you guys remember when we did big O and big omega, we did the substitution method. In the substitution method, we said, unlike the master method and the recursive tree method, we said that assume that you are trying to prove this is big O n square, and then insert that n square into the equation and see if the equation still holds, then it is big O n square, otherwise not, right? So that is the idea. We are going to assume that E is a solution, that we want to assume that X is currently a solution. We want to add E to this solution. If E already exists in this X set, then there is nothing to prove, it is true. But if E is not in this tree, then you will construct a different minimum spanning tree T prime, where we are going to add this edge to the set of edges. We are going to be altering the original tree by creating this T prime by adding this edge, just one of its edges. And then once we add it, we know that we will create a cycle. Can you guys tell me why? If T is connected, means that all vertices have been connected by this tree. So that means that this is basically, let's say, the blue nodes. The blue edges is the tree, and that is connected. The question is, do you guys agree that adding one more edge, whatever edge, will create a cycle? One more edge creates cycle. Awesome. So that is what this says, that since T is already connected, it is already has a path between the endpoints of E. So adding E creates a cycle. Okay. So this cycle must have also have some other edge E prime across the cut. There is a diagram like this. You have added E. Since it has created a cycle, do you agree that there must be one more edge that was existing in the previous solution that is basically the contributing factor of this cycle? So all we now have to do is, since the cycle has come from some other edge E prime, we will say from the original tree, or sorry, in the original tree, we are going to add our new solution edge, that is the number 10 from this min coin change problem. And we are going to remove the previous edges or the other edges that are creating a cycle. So T union of E, subtraction of E prime, which we will show how to be a tree. How? Because since T prime is connected by property 1, since E prime creates a cycle, if I remove that cycle properties 2 and 3 by that thing, it is still going to remain a tree, because removing a cycle creates a tree, right? It will not create disjoint graphs. Removing a cycle means there are two paths to the thing. So removing one of those edges will get us a tree. So how do we do that? Well, literally speaking, we will compute the total cost of this new tree by just computing this, which is, if we go back to our checklist, is what I want you guys to prove things with. That is cost to remove the part, cost to add the part, and sometimes cost to adjust the solution to the new part. That is, from the overall weight of the original tree, I'm going to be adding the weight of this new edge and subtracting the E prime bit. Which previous one, the greedy proof checklist one, or why is it a tree part? Sandhya? So I'll just go over this thing again. Hold on. So what I'm saying is, the checklist one. The checklist one says, checklist one, we will talk about it properly, but we will need to provide, when we are proving for greedy algorithms, we will need to provide this cost analysis, that adding our solution to the problem, adding part of our solution to the problem, removing the cycle bit from the problem, and maybe doing this might require some adjustment. So we will add up the three costs, and this cost has to be lower than the actual cost. That is what this says. That is, we are to the original tree's total sum of the weights, we are going to add a bit of edge with our own weight and subtract the solution of the E prime weight. This new weight of T prime, in order to prove that weight of T prime is the better one, we will say that both E and E prime cross between these two sets, S and not S, right? So both E and E prime cross between two sets, right? They are the ones that are creating the cycle. And we are removing one of them. We have assumed, our greediness has assumed that E was the lightest edge, right? We are trying to add this dotted edge E, and this E is the lightest edge across these two sets. E prime has a larger cost. So if that is the case, is the same math that we did earlier, is the same math here when we did 16 and 13 and that 16 plus 3 minus 2 thing. It's essentially saying that since weight of our edge by definition is less than the edge that is in the previous solution that is creating the cycle, then the sum of all weights will also be less than the original tree's cost. Do you guys agree with this statement? If you do, that is the major point in greedy algorithms. You have understood that. Remember that E, so E prime is in, let me type it in the notepad. So E prime is already in current incorrect MST. Let's call that tree T. What you are saying is we are going to add E or pick an edge E that is the edge with the lowest cost across the cut. What cut? The E prime cut, right? So if E has the lowest cost, by definition then, weight of E or the cost of E has to be less than or equal to the cost of E prime. Do you agree? Because E, weight of E, we assumed is the lowest cost thing. So since it is the lowest cost thing, it will be lower than E prime as well, right? So if this is the lower thing, for the original tree, what was the cost, total cost? Well, it was the sum of all such weights, right? E underscore I. This was the sum of all weights. Now, if we compute this new tree T prime, what is the cost of this new tree T prime? Well, currently the cost of the new tree T prime is the cost of the original tree. So we will say capital W of T plus the weight of this new edge that we created. Remember, by the way, this capital T already contains the E prime thing, right? So includes weight of E prime, correct? So essentially this includes the weight of E prime and we are adding this cost. Now, since this is going to create a cycle, so it is no longer an edge, we are going to subtract out the cost of this WE prime. Do you guys see that if that is the new WT prime, can I now claim WT prime is less than or equal to W of T? Let me type this out in the chat. Why? Because the total cost is, okay, so let's take numbers. Let's say that we are picking an edge with weight 3 and which is less than or equals to some weight H E prime. So let's say that is 5. Now let's say that the overall cost we are trying to compute for W of T prime. Let's say that currently the total tree cost is somewhere around 20 or something, right? And what are we saying? We are saying plus add our edge cost, so that is plus 3. That also includes the WE prime. So let's say which is 5, but then we are going to subtract out 5 from this thing. Do you guys agree that this new tree will be less than 20? So if it is less than 20, obviously because of this surgery, we have made the cost go down. So your solution is now better than the assumed solution. And that is how the proof mechanism works for both Kruskal, Prim's and other algorithms. Okay. Okay. So let us go through this thing using Kruskal's algorithm. But essentially what this is saying is, let's say we have this set, and we are considering this edge. CE is the current edge. D is the other edge that we are considering. We can easily swap, sorry, the first edge is this particular cut. From here we are checking BD, CE is later, EF is there. So essentially we are adding BD here, and then after that the cut becomes along these lines. So from here we are adding E. From here we are checking if we should be adding CE or not. Well, CE and DE, I can pick any one. DF will actually increase the cost, so I'll be picking one of these two, right? So Kruskal's algorithm works as follows. At any given moment, the edges it already has chosen form a partial solution. Let's go and look at the visual again. This is Kruskal algorithms. At any given point in time, the edges that it has chosen form a partial solution. A collection of connected components, not a single connected component, a collection of connected components, each of which is a tree structure. So it's a collection of connected components. It's a collection of different connected components, each of which is a tree. Compare that to Prim's algorithm, which is always a single connected component growing outwards. Kruskal, on the other hand, is more akin to a collection of connected components. I have a very weird question. I would love for you to answer this thing. Insertion sort, comma, selection sort, Kruskal's way, comma, Prim's way. Can you say which one is what in some weird scenario? Can you compare these two sorting algorithms? Can you say Kruskal is like insertion sort, or Kruskal is like selection sort, and Prim is like insertion sort, or Prim is like selection sort? Think about that. That would be a fun exercise to think about. Cool. Think about what would you need. Are you detecting the minimum every time? Can it work with which one can work with an online input? Which one can work with, which one needs an offline input, in a sense. So the next edge E to be added connects two of these components. Let's call them T1 and T2. Right, I forget which one was selection, but the one that computes the full minimum first and then adds the thing, that's more like Kruskal. Prim is like only the minimum so far. So I think that one is insertion, more or less. You guys are correct. Exactly. I'll have to double check selection and insertion. I confuse. But yeah. Yep. You're right. Since E is the lightest edge that does not produce a cycle, it is certain to be the lightest edge between the two cuts. Therefore, it satisfies the cut property. Now we fill some implementation. So here's the thing. Firstly, you are sorting all the edges, and then you are adding these edges to the current partial solution. But the major thing to check is to check if a candidate edge is going to create a cycle or not. How do you check for that? Well, essentially what you do is for each of these trees or subtrees of Kruskal, let it reset a bit, I'll come back. But each of these subtrees is going to be maintained in a set. So we have 3 sets so far, fourth set, 5 sets, 5 sets still, 6 sets, 7 sets, 8 sets, and each time we are either increasing a new set or we are now decreasing sets. We are merging different sets together. If it creates the cycle, that is, you are adding an edge between the same set, that is the starting node and the ending node belong to the same set, like for this one, right? Starting node and ending node belong to the same set. That is how we detect for cyclicity. Okay, so we are going to maintain multiple sets, and if the edge that we are considering is basically edge between two vertices in the same set, then it creates a cycle. So we are going to skip that edge. Marcus, I'm going to properly look into the insertion selection difference and I'll update you, but I think you guys are correct. This one. Okay. So that is the point of learning the set mechanism. So initially, each node is going to be in a component by itself. So if we have V vertices, we will have V sets. So we will just call a make set operation that will create each V sets. That is just, I think, we go V time complexity. Then we have to repeatedly test pairs of nodes to see if they belong to the same set. So we will say find x, that is x is an edge. Oh no, x is a vertex where we are asking, hey, who do you belong to? Who's your set? Now, whenever we are adding an edge, we are merging two components. We are going to union two vertices, x and y, because that is what an edge is. So all we need to check is find x, get the set of x. Find y, get the set of y. If those two edges are the same, those two sets are the same, ignore. If not, perform an union operation, right? So one way to store a set is as a directed tree. Each time, let's say, so for example, these two trees represent two sets. One is BE and one is the set ACDFGH, this set. Okay. Now, how do we use this as a set? Well, the root element is going to be the representative of your set. So you are going to ask, hey, what is the set of B? You say E. You are going to ask, hey, what is the set of G? Well, the set of G is H. What is the set of F? Well, that's H. What is the set of A? H. C, H, D, H. So the root node is your name for the set. So if you are now asking, should I be adding edges between D and F? Well, you are going to ask, hey, what is the set of D? Well, that's H. What is the set of F? Well, that is H. So both of those are basically the same set. So we are not going to be adding the thing. Okay. So if that is the case, and if you have this G, do you guys see that more or less you will need log n comparisons to check the root node and essentially figure out the set given a tree, right? We have discussed this. Given a tree, if I want to, like the heap tree thing, given a tree, I would like to go up the thing and figure out who the root node is. I could also maintain the root node, but I have to check which edge belongs to which vertex belongs to what root node. And there is a trick of solving this thing much better. So we will talk about that in a bit, but we maintain a rank and a parent thing. That is the height of the tree. Yes, Marcos. So we will say that the initial root node has a rank of 0, and we are just going to find the thing. Let me show you the example that I'm talking about. We'll come back to this code later. Okay, so initially, let's say these are the vertices A, B, C, D, E, F, G, and we are basically trying to create individually each of their sets. Each of them have a number on top. That is the rank of the tree. Rank is in essence the largest height below this node. The largest height below these nodes are all zeros, so we are skipping. Now let's say we want to union A, D, B, E, and C, F. Well, we will add A to some node, either D or think both of them have the same rank. If both of them have the same rank, then what did we do in the code? Well, if both of them have the same rank, so not this part, the else part, if both of them have the same rank, that is less than or equal to, we will pick one of them, make one of them the parent of the other, and set that one's rank to +1. Okay. Randomly pick one of them. So A and D, we pick D, A, let's say A gets to be the child of D, B gets to be the child of E, C gets to be the child of F, D, E, F now have a rank of 1. G still has 0. Now let's say we want to combine CG and EA. Okay, so CG would require that we are combining G into this tree here, CF. And EA would require that I'm going to be adding this edge. So we have to combine these two trees into this tree here. Now comes the point, which ones should you be adding to? Okay. So if both of those ranks, do you see that I'm asking for CG? So I'm asking for EA for now. Let's do EA. I asked for E and it tells me E is the set. I ask for A and it says D is the set. So both of them are two different sets. Both of them have the same rank. If both of them have the same rank, then pick one of those trees and make E1 the child of that tree and make D into D2. However, if both of them do not have the same set, I mean, do not have the same rank, So for example, CF set is F, G's set is G, G's rank is 0, F's rank is 1. If that is the case, where would you like to add G? Should I be adding F under G or should I be adding G under F? Can you guys tell me that? F under G or G under F? Why, Zach? What would happen if we did F under G? What would be the rank of the thing if I do F under G? Do you guys see, if I do F under G, rank becomes 2, right? So why do we want to minimize rank? Because of log n, because of height. We want to traverse to the root node. So we want the shallowest possible tree ever, right? So that is why if you look into the code, if one rank is more than the other, we are always going to make the parent of the lower rank equal to the one with the larger rank. That is what this says, right? So essentially that happens, and we have a D2 and an F1. F1 needs to be added below D2. That way D2 still remains as it is, the rank remains 2. And that is how you create a set. Makes sense? With a rank thing. Time complexity wise, sorting is going to take E log V time of E edges and V vertices because there are double vertices and there are total of V make set. I'm going to create a make set of individual vertices one by one. Finding the set of the thing is twice the number of edges in the worst case scenario, and combining two things requires V minus 1 union operations. Overall, they would take E log V time. Now, it can also be done much quicker if we do a proper sort, but other type of sorting algorithms, counting sort and whatnot. But instead of that, what I want us to check out is we can also use a data structure like this. So if going to the root node is the biggest hurdle, why not maintain some additional pointers like literal C++ pointers in your data structure, where every node here in this format, in the previous format, every node was pointing to its own parent and then its own parent and you go to the root. But why not have B also point to D, C also point to D, G also point to D. That way, everyone is going to point to that thing. It will come at a cost of space. What cost would that be? Well, the number of vertices, I would need that many extra pointers. So the space complexity increases by that. But I am now going to get a much reduced time complexity. Looking up or the find operation is now going to just become a constant time complexity, right? Because I'm just going to, so find operation can now be done in constant time complexity, right? And union is also easy enough. It's just merging those two. So we can make some more optimizations to basically implement this particular thing. And overall, this is the time complexity of this thing. We are going to go over this more properly about the time complexity analysis of this thing. Today, we are just discussing about the overall view of the thing. Okay. Now, next comes Prim's algorithm. I am going to discuss Prim's algorithm a bit, but we are going to discuss Dijkstra's algorithm, then Prim's algorithm. Say hi to the relaxation function again. The only difference, can you guys tell me what is the difference between this function here and the relaxation function that we have been discussing so far? Remember, when we did the greater than thing for the relaxation function, it was always, where is the Cornell book? Where was Bellman Ford? Right. So if you guys remember, this was the relaxation function, and it was always v dot d greater than this entire sum, that is cost from source to the current u node plus the weight of u to v. Do you see the difference between that and this particular cost, where the cost is greater than just the U to V cost or just the V to Z cost, and you're assigning that as the cost. That is the difference between Prims and Dijkstra. Dijkstra also grows like this step by step. Prims also grows like this step by step. Dijkstra also looks at outgoing edges. Prims also looks at outgoing edges. We can also look at that when we see the slides for Dijkstra. So let's go to BFS algorithms. And you remember this was the slide for Dijkstra, right? It was growing outwards and it was checking all of these edges. The thing is, it was picking this edge because this edge, this vertex V had the smallest cost from S to V via U. These and these and these are not the smallest cost from S. Compare that to what we are doing here, where we are just looking at this edge, not the total cost, if that makes sense. Okay, this is how Prim's algorithm works. It's literally related to Dijkstra's algorithm, literally the same time complexity as of Dijkstra's algorithm. Both of them end up having that log. Dijkstra was sorting using a priority queue. Kruskal is sorting using a complete sorting algorithm, whichever way works best, right? Depends upon your problem of choice. If your data is coming in over time, you would prefer what? Prims or Huffman? Sorry, Prims or Kruskal. If your data is coming in over time, then I will not be sorting the entire thing. I would prefer Prims. If I have the graph already, I would prefer Kruskal. Do you guys agree? All right. So we are going to discuss this a bit further, and we are going to use the Huffman coding example properly to understand the the cut property. And then we are going to look at set cover, which is not a greedy algorithm. So set cover is a very important problem, like vertex cover, knapsack and stuff, where vertex cover problems. We'll come to those when we do NP hard problems and stuff. Set cover is not a greedy problem. However, there is a proof that, and it was a very interesting proof. I used that in one of my research areas at one point, that even if I am doing greedily, how bad can I be if I do greedily? So I know it is not the optimal solution. Optimal solution was N, but if you do greedy, how bad can it be? Well, the bad part came out to be n log n. So log n was then the optimal solution. So that also comes in. We will discuss Huffman coding in a proper detail later next class. But what I want us to look into now a bit is the book's Huffman coding example, which is in the greedy algorithm section. So chapter 15, I believe. Yep. So Huffman codes are here. And essentially, I'll be discussing this Huffman coding example later, but you will see how they prove Huffman coding. By the way, have you guys ever heard of Huffman coding? Some of us have. Anybody who has not heard of Huffman coding? So essentially, we will be looking at Huffman coding. Yes, so Huffman coding is a mechanism to compress data. Okay, so imagine a song MP3 file compression or whatever compression. We are going to compress data by learning one thing, that certain characters are more frequent than other characters. So for example, in English, the letter E is much more frequent than the letter Z. Right. So maybe we will use less bits to encode E, more bits for Z. Is there a balance that we can sort of manage that will allow us to prove or do that thing that, basically reduce the total overall cost of the thing? I just want to show one thing and we are done for today, is this. Here is how the proof of Huffman coding looks like. This is in page number 437. And you see that it is creating a tree, subtracting the tree, the new tree, and it is showing that the old tree had a larger cost compared to the new tree. It is computing that with respect to the cost function and subtracting that this tree's cost function with this tree's cost function, expanding that out and then solving it. That is the type of proofs that we are going to be doing, and we are going to be submitting those proofs using this sort of a checklist of mine. We will be discussing that with random lead code problems and a few code force problems as well. But yeah, that's it for today. That was your introduction to greedy algorithms. Sandhya, very good question. For assignment 3, where I ask you for question 1, adding functionalities to the existing code, please submit a separate Jupyter notebook as your submission. Do not submit a link to the code. Download the Jupyter notebook, write up the thing, and then submit it separately. Okay. Cool. If that's that, thank you guys so much. I'll also be posting this video. I swear I will figure it out by tonight. I'll also be grading by